So I want to resume our discussion on second order asymptotics in the context of lossless source coding. Okay, so what is lossless source coding? It's basically compression and lossless source coding. Okay, so we will take the simplest approach. Everything is fixed length. Okay, so you might have encountered this in chapter 3 of Cobra and Thomas, and the setup is as follows. So we have a source X, and say we have n copies of it. This source is distributed according to P, okay, and we want to somehow compress the source, that is to encode it using some function. We want to encode it to NR bits, okay. Another way of saying that is we want to generate some random variable that can only take on a certain number of values, and we then want to do the reverse operation and to come up with an estimate of the source, x hat n. Okay, so this is a compression problem, and we want to find out what is the minimum number of bits that we can use to compress, that we should use to compress the source. Okay, and of course we measure the goodness of our compression algorithm by the probability of error. Okay, the probability that xn is not the same as x hat n. Okay, so we are going to assume that everything here is discrete, so it makes sense to talk about probabilities of error. Okay, so if xn is continuous, then we have to adopt the rate distortion approach. Okay, but we will not do that today. So we will define formally an m epsilon code for the source Pn. So this is the distribution of the source Xn as consists of number 1, an encoder. Okay, so there's an encoder f that takes us from script Xn to m, and the reverse operation. Okay, the decoder that takes us from m numbers to xn. Okay, so these are the two very basic operations that we will do. Okay, that we have to design for an m epsilon code. Okay, so m represents the number of reproduction symbols here, and epsilon represents the probability of error. So n epsilon code basically means that the probability of error does not exceed epsilon. So that probability of error can be written as x and x, such that xn is not the same as the reproduced symbols. So that is the mapping under the encoder, and then and what is produced after m goes through the decoder. All right, and we ask the question whether that is the same as xn or not. If it's not, then there is an error. Okay, so that is the probability of error should be less than epsilon, less than or equal to epsilon. So that is the entire source coding setup. Okay, that's exactly what is lossless source coding. So we want to ask the same types of questions as we did previously. Okay, and what are the sort of questions we want to ask? Well, we want to actually minimize the total number of reproduction symbols here. Okay, so we want to define some type of measure for us to fix the error probability epsilon and to minimize the total number of symbols. Okay, so let us define this very important quantity. Okay, m star. So m star again. So we are overloading symbols at this point, but this is for source coding. It should be clear. So m star depends obviously on the source p, as well as the permissible error probability epsilon. Okay, so we make this notation very clear. This is the source, and this is the permissible error probability. What is this? This is defined to be the minimum. Okay, so in source coding, what we want to minimize? We want to minimize m, which is an integer, subject to the condition that there exists an m epsilon code for p, for the source p. And this object here has already been defined, exactly here. Okay, so this is some quantity that we want to get a handle on. And what do we already know? Okay, what do we know? Well, we know a lot about this. Okay, and in particular, Shannon, in his seminal paper, used typicality arguments to show the following: 1 over n log mn, m star p and epsilon, that is the first order asymptotic expansion, equals to the entropy. There's a limit missing, and here it is. Okay, and this holds for every epsilon between 0 and 1. Okay, for a discrete memberless source. So the units for entropy are, of course, bits per symbol. Bits per symbol. Okay, and this quantity is, of course, our familiar entropy, which many people write as h of x, and sometimes I do too. Okay, but and it's defined in the usual way. Okay. Okay, so this is exactly what we already know. Okay, and what is somewhat not so obvious and familiar to some members of the audience here is that this limit here does not depend on epsilon. So again, by writing it in this form, by writing the result in this form, we have actually stated a strong converse. Okay, if you do not know what it means, it's okay for now. All right. So this, in another way of saying this, is that there exists a sequence of 2 to the nr epsilon codes. Okay, for which for the source Pn, for which the epsilon can be anything between 0 and 1, as long as the rate r is above entropy. Okay, so that is Shannon's theorem, Shannon's source coding theorem. Okay, so another way of writing this is the following. Okay, so before we rewrite that, the interpretation of this is that entropy is the smallest exponent for sets in Xn with Pn probability at least 1 minus epsilon. Okay, so with probability according to P, okay, the probability must be higher than 1 minus epsilon. What is, then we can ask the minimum size of the exponents of such sets. Okay, so that is that. Another way of writing this is the following. Okay, so if I just look at a logarithm of the minimum code size, so that's known as the minimum code size. All right, if I can tolerate an error probability epsilon and the source is realized n times, then what I get is n times entropy plus little on. Little o is some function that is smaller in some senses. Little o means that this quantity here divided by n goes to 0. Okay, so that is another way of writing that statement, and this holds for every epsilon. So this leads us immediately to wonder, okay, what is the remainder term? What is the remainder term? Can we quantify it in a more precise fashion? Okay, can we quantify the remainder term in a more precise fashion? And hopefully the answer is yes. Okay, what is the remainder term? Okay, so now we will try to develop two small little bounds, two very simple bounds on m star p epsilon that will allow us to determine the remainder terms in this asymptotic expansion. So n of hp is known as the first order term. We would like to determine what are the remainder terms, so that is the first order term, and what are the remainder terms. Okay? Alright, so the first lemma is an achievability lemma. Okay? So achievability. Okay, what does this mean? Right? So we want to place bounds on m star p epsilon. And achievability in source coding means an upper bound for the minimum size of block codes. Okay, minimum size of the source code. So for every source p and every epsilon between 0 and 1, I will not state these. This is upper bounded by beta 1 minus epsilon p mu. Alright, so beta is the familiar beta function I talked about in hypothesis testing. P is the source, mu is undefined. right? So I owe you this definition. All right. So mu here is the counting measure. What is the counting measure? Counting measure, basically, you have a source and it has some alphabet. Now, if you apply the function mu or the measure mu to any element of the alphabet, you return 1. Okay? So this is not a normalized PDF per se. Okay? This does not add up to 1. So we are abusing notation here. All right? We are saying that, okay, the arguments of beta are usually take on probability mass functions only. But here we are allowing some freedom to choose the second argument of the probability mass function to be something other than the second argument to be something other than a probability mass function. In fact, we choose it with a counting measure. So counting measure means that i.e. mu of x equals to 1 for all x in x. Okay. Right. So and furthermore, okay, really mu of a equals to size of a for all a subset x. Okay. Okay, so that is an achievability bound, right? So that means that this is something that is that can be established quite easily. Okay, how do we show this? We will show this by some very simple arguments. All right, proof. Okay, so let us take any set. Let us consider any set T subset of x, okay, such that P of T greater than 1 minus epsilon, okay? So now let us try to minimize over all possible such sets, okay? So this set is a good set, okay? We are going to encode all the realizations of the source x, okay, that belong to this set. So you can think of this set as a typical set. Okay, this typical set has probability greater than 1 minus epsilon. Now let us then consider all possible such sets. Okay, now clearly there are only finitely many such sets, so I just have to take a minimization. I just have to take a minimum over all possible such subsets. Okay, that satisfy the constraint. Okay, and the source code, other way around, greater than 1 minus epsilon. And the source code will have size exactly that set. Okay, so this provides a very simple bound for the minimum size of block codes with P probability at least 1 minus epsilon. Okay, now if we stare at this expression for a while and we think of this and we can basically rewrite this in terms of the counting measure. All right, so this is exactly the counting measure, mu of P. If you stare at this for long enough, you will notice that this is exactly beta 1 minus epsilon P mu. So in other words, we are encoding everything, all the sources in T, throwing out everything else, and we are searching over all possible subsets with that high probability. High as in larger than 1 minus epsilon. So that is a very, very simple proof. It's really quite trivial. Okay, so that provides an achievability bound for source coding. Now, the converse bound I will not prove. Okay, it requires a little bit of effort. Okay, which I will state here. Okay, so that's an achievability bound, and the converse bound is as follows. Okay, converse. So before we state anything, I just want to say that lossless source coding, all right, and hypothesis and binary hypothesis testing, as we have seen just now, are very, very much related. In fact, they are one and the same if you choose the measures, the probability distributions appropriately. And you have to generalize the second argument to the counting measure. So the converse bound is again intimately related to hypothesis testing. So converse bounds in source coding imply a lower bound to m star or log m star. Okay, and we can rewrite this in terms of the information spectrum divergence, or rather the negative information spectrum divergence. Okay, eta here is any number such that choose any number eta such that epsilon plus eta is less than 1, or in fact eta is between, say, 0 and 1 minus epsilon. So as usual, we have done this before. This is P, mu, and some constants. log 1 over n. Okay? So, as we can see here, the fundamental limits, the non-asymptotic fundamental limits of source coding are intimately related to the hypothesis testing divergence as well as the information spectrum divergence. So whatever expansions that we have developed just now carry over directly to this setting of lossless source coding, because we have established an upper bound and a lower bound for m star, the minimum size of block codes. So now what is the next step? Once we have established such non-asymptotic bounds, the next step is to consider n repetitions, n is large, n repetitions of the source, and to develop some sort of asymptotic expansion that refines the remainder terms in that asymptotic expansion. Okay, so we know that the first term is entropy. Shannon said so. What are the remainder terms here? Okay, in fact, whatever I'm talking about now, as I mentioned previously, is written down in Strassen. It was a bit difficult to parse, so now hopefully this is slightly easier. Okay, so now let us try to state the asymptotic expansion for source coding. All right. For any discrete memberless source, discrete memberless source, P, okay, with say, just to keep things simple, Vp greater than 0. This is undefined for the moment. All right, deliberately undefined. Okay, this is some measure of the source. Okay. For any discrete memberless source with the var entropy, this is called the var entropy, or the source dispersion if you wish, var entropy. Okay, with var entropy greater than 0, we have the following asymptotic expansion: log m star Pn, so that is n repetitions, n independent and identically distributed repetitions of the source. That is, the first term is well known, the second term is perhaps not so well known. Okay, V inverse epsilon plus O log n. Okay, so what is the interpretation? Now, if we write this in terms of Q functions, and maybe we can do so right here, then things will look a little bit nicer. So if we write this in terms of Q functions, and epsilon is small, say 0.01, that means that at finite block lengths, we need to operate at a rate that is higher than entropy by this amount divided by n. Okay? So if we divide everything by n, we see that we divide this by n as well. So the pre-constant in front of the Q inverse function is the var entropy. Okay, so this is the price we have to pay if we want to operate at finite block lengths, and we cannot use the source many times. Of course, you can compare that to the finite block length bounds, which in some cases can be computed. Okay, so I want to now go back to the phi function because I'm more comfortable with that, but you can do everything in terms of the Q function, no problem. Okay, so what is the var entropy? Well, the entropy is defined there, where's the entropy? The entropy is defined there as the expectation of the information. Okay, it's the expectation of this log of 1 over px, which is the information random variable. The var entropy is nothing but the variance of the information random variable. This is capital X, and just to spell it out a little bit more clearly, this is log of 1 over px minus the entropy. Okay, so that is the variance of that random variable according to P. Okay, so given what we have already learned from hypothesis testing, it is not so difficult. This can be proved in one line, all right, which we will do right now. So are there any questions on the setup? Are there any questions? So of course we need the source var entropy to be positive, otherwise things don't work. I mean, things become a bit pathological. Okay, stop. Okay, right here. Okay, so now what we want to do is to provide a short little proof, okay, of the asymptotic expansion based on what we already know. Okay, so this actually, as you can see here, where's the? So this actually answers this question. What is the remainder term? The remainder term are all these things involving V, the source bar entropy, as well as the Q and also V inverse function. Okay, so that provides a refinement of Shannon's source coding theorem. Okay, so all these things refine Shannon's source coding theorem. Okay, so great. Now let us provide a very short proof. Okay, so let us first prove the upper bound. The upper bound uses the achievability bound at the top left-hand corner here. So if I consider n repetitions of the source, Pn epsilon, then I will take the log of the beta function appropriately, and I will basically insert Pn and mu. Okay, so that is exactly the upper bound. Okay, but we know something. From hypothesis testing, we know what is the asymptotic expansion for beta, or minus beta. All right. So this is exactly equal to, what is that equal to? Minus divergence, P. But now we have to be careful. This is not Q. This is the counting measure. All right. So we basically insert the counting measure here. All right. And that was minus, right? Minus root and Vp. This is the relative entropy variance. Okay, from the discussion just now. V inverse epsilon and O log n. By the way, it is relatively easy to refine this even further. This, in many cases, this will be minus half log n in the source coding setting. Okay, and again, this carries over, the result for this third order term carries over directly from hypothesis testing. If we had refined our result in the third order term for hypothesis testing, it's very easy to refine the third order term for source coding. Now, then we have to ask ourselves the question, what is this object and what is this object when the second argument is the counting measure? So if we plug P and mu into the definition of entropy here, P and mu into the definition of the divergence, okay, we see that this is exactly minus entropy. Okay? So this is exactly, this part here is exactly minus entropy. And this is, okay, if we play the same game, this is exactly the variance of the variance of the information random variable or self-information random variable. So this reduces them exactly to the result for discrete memberless sources. So this is a one-line proof of the upper bound. Okay. Now the one-line proof of the lower bound proceeds exactly similarly. So we have log of m star from the converse bound. Where's the converse bound here? Pn epsilon. Right. Well, we need to expand the information spectrum divergence. Okay? And the information spectrum divergence can be expanded. We have a result for that. Alright? Just now we had a result for that. So ds epsilon plus eta, p and mu, and log 1 over eta. Right? And again, as is usual in these sort of exercises, we usually take eta to be 1 over root n. This is the rule. So this becomes half log n. 1 over root n. Half log n, right? 1 over root n half, minus half log n. Yes. Okay. So but we have an asymptotic expansion for ds. We have an asymptotic expansion for ds. And the asymptotic expansion for ds is very much like dh or minus log beta up to some minus sign. So we can believe that this first term is also equal to entropy. The second term is a function of the bar entropy, phi inverse epsilon, up to some O terms that we will not care about in this tutorial. So that proves the upper and the lower bounds. So as you can see, if we understand hypothesis testing well enough, we have the tools to do source coding, and as we will see very shortly, also channel coding. So I took about 20 minutes to talk about source coding. Are there any questions?
Vincent,
Yes.
in the converse lemma,
Yes.
the right-hand side term looks like the upper bound for the dh, which would be
Yes, exactly. Exactly.
Yeah, except you get log 1 minus epsilon something.
Yeah, maybe I forgot about the log 1 minus epsilon, but that is inconsequential. So really, you can express this in terms of dh as well.
Yes, and then you...
And then it's really exactly the same, right? Okay, so great. So we have seen the similarities between lossless source coding, fixed length, variable length. There are many other complications. We have seen the similarities between fixed length source coding as well as hypothesis testing. So now we want to talk about the most important topic, which is channel coding. And this is going to be quite involved. Hopefully most of you can follow most of the arguments. Okay. Are there any questions? Or erase the board. And again, in channel coding, familiarity with hypothesis testing is important because the non-asymptotic bounds will be stated in terms of DH, DS, and things like that. Okay? So once we have established that, we just have to play some games and look at the asymptotic expansions that we have developed in order to talk about the asymptotic expansions for channel coding. Okay? But in channel coding, there's a problem. There's a major technical problem in that we have an optimization over the input distribution. Okay? And that can cause some problems. We have to do some analysis, some continuity arguments that I don't think I'll have time to talk about, but you can read my monograph if you want more details. Okay? So, channel coding. Yeah. Okay, so what is the channel coding problem? Okay, in channel coding, we would like to transmit some message, alright, which we will denote by M. This is some random variable. It's not to be confused with the number of code words. Unfortunately, there's a conflict here. Okay, and we will encode the message using some encoder, and this will give you some code word. Okay, and say we use the channel one time. My channels are always W. Okay, and what you get at the output is Y, and you use the decoder to decode to look at Y, and you give an estimate of M, which we call an MPEG. Okay, so that is the setup for channel coding, and you would like to design these two boxes, F and phi, so that the probability of error is maximized and the probability of error is minimized and the rate is as large as possible. So we're trying to make all these precise. So an M epsilon average code, this AV stands for average. We will see that this can be changed a little bit. An M epsilon code for channel W. So this W maps X to Y in a stochastic manner. Okay. For the channel W, consists of an encoder F that maps M messages. Here M is a number. So there's a conflict in notation, I know, but it's okay. It's a number, an integer, to code words, to the code word space, and to a decoder which maps the output of the channel, Y, there's no N at this point, to the code word space. So the message set. Okay, sometimes some people allow erasure symbol, but here we don't have to allow. Okay, so great. So that's the setup. What is the epsilon? Epsilon is the bound on the average probability of error. And how do we write the average probability of error? We basically take the average over the conditional probabilities of error. How do we write that? W of FM. So we send code word M. All right. But we decode it to some code word, some message that is not M. How do we write that? We basically take the inverse. We look at the code word space Y, take away phi inverse M. Okay? So we decode it to some message that is not M. Right? Phi inverse is the decoding region. Phi inverse M is the decoding region for message M. This is less than or equal to epsilon. So that is a fancy way of writing the probability of error. You can just write it as such. Probability M hat not equal to M. Okay? But that way, this way of writing the probability of error, it makes clear that this depends on the code, and depends on the channel, and depends on M as well. Alright? So that is the exact setup. Cool. So in channel coding, we want to maximize the total number of messages that we can send. Alright? So it makes sense to then define the following non-asymptotic fundamental limit. It makes sense to then define M star F. Sometimes whether we use the average probability of error or maximum probability of error makes a difference. Okay, so we will, in this entire tutorial, talk about the average probability of error. Okay, M star W epsilon. So this is the maximum number of code words we can transmit across the channel W with average error probability no larger than epsilon. Is written mathematically as follows: max M such that there exists an M epsilon F code for W. So that mathematically is written as follows, okay? And again, just as in the source coding case, we want to examine asymptotic expansions for this object. But before we do so, we have to let something go off to infinity. And in the channel coding case, we will let the users of the channel go off to infinity, all right? So we will take W, the channel, to be n users of a DMC. I.e., that means that the input symbols are xn, and the output symbols are yn, okay, n copies of the output space, and n copies of the symbols in outputs, n copies of the symbols inputs, okay, and they are related as follows. Okay, so this is a DMC. The input space is finite, script x is finite, the output space is finite, okay, just to keep our discussion simple. And the channel evolves according to this stationary membreless fashion. Okay? So now the question we want to ask is, what's the behavior of log M star Wn epsilon? So now the channel is being replaced by one big channel, DMC, okay? N users of it with error probability epsilon. Okay? What is this? Okay? Equal to. So that is our object of study for the next 1 hour before we take a break. Okay, now a very natural question is, what do we already know? Alright? Just like in the source coding case, we ask the question, what do we already know? And what are we after? What are we trying to refine? So here, let us take a theorem. Shannon. Okay. Together with Wolfowitz's strong converse. Okay. So we already know that for DMCs and for epsilon between 0 and 1, I will not state that, the following limit exists. This is not obvious at all. M star AV Wn epsilon equals to C, channel capacity. And C here, channel capacity is defined in the usual way, max P IPW. Okay, IPW is another way of writing IXY, where we make the distribution and the channel explicit. Yeah, that's the way I like to write it. Okay, so i.e., this means that we can transmit up to C bits of information per channel use. This is usually positive, so we can transmit at positive rates. Okay, so another way of writing this, okay, is the following. Log of M star AV Wn epsilon is equal to NC, okay, plus little on. Just as in the source coding scenario. So the question now we want to answer is, what is the remainder term? What are the remainder terms, as a matter of fact? If you are more ambitious and you want to talk about the third order terms, what is or what are the remainder terms? This. Okay, so that will be our agenda for the next 1 hour. I'm not sure whether I can get through everything, but we will try to prove some stuff, we will try to skip some stuff. Okay? So the agenda is as in the source coding case. We will try to state some non-asymptotic bounds, okay, for the direct part, for the achievability part, and we will try to state some converse bounds for the converse bounds, and then we will insert the channel W and replace it by Wn. Then we will let n run off to infinity, and we'll see whether we can evaluate the remainder terms. So that is the agenda for the next 1 hour. Okay? Are there any questions on the setup for channel coding? I believe this should be familiar to everybody, if you have taken a first course on information theory. So you can transmit up to, you can transmit up to C bits per channel use. Okay, what is perhaps not so difficult is the achievability part. Okay, how can we achieve an asymptotic expansion, how can we achieve the dispersion, if you may, the second order term? Okay, the converse part requires some ingenuity. Okay, the forward part, the direct part, is not so difficult. And it's based on something called Feinstein's lemma. There are many ways to prove the direct part. There are many ways to prove the converse part. What I'm going to try to show you are the simplest ways to get to the second order term. Okay? The simplest ways, in my opinion. So the direct part, or the achievability part, is proved using Feinstein's lemma. Feinstein's lemma, 1954. Okay, so let us try to state Feinstein's lemma. Actually, it's not quite Feinstein. What I'm trying to say is not quite Feinstein's lemma, but I'm just going to call it Feinstein's lemma anyway. Okay, lemma. Feinstein. Okay, this is not quite Feinstein's lemma because Feinstein's lemma works for the maximum probability of error. This, I'm going to state a weaker version for average probability of error. Okay, so let's call it the Shannon bound as well. Okay, so this basically says the following. Now let epsilon be a number between 0 and 1. Let W be any channel from X to Y. Doesn't have to be a discrete memberless channel. Later we will specialize things to be a, later we will specialize W to be a discrete memberless channel. It doesn't have to be a discrete memberless channel for now. Okay, and again, let eta be some number between 0 and epsilon. Okay, epsilon is between 0 and 1, so you can choose such an eta. As usual, later we will choose eta to be 1 over root n. Okay? And so Feinstein's lemma, or the average error version of Feinstein's lemma, says the following. Okay, so it places A. So this is the achievability part for channel coding. You can achieve something, which means that you place a lower bound on the number of code words. Okay, so this is the correct way of stating Feinstein's lemma. Okay, it's a lower bound on the maximum number of code words. It's different from the source coding setting. Okay, so what is this? You can optimize over input distributions of what? ds epsilon minus eta. Okay, so you have control over the input distribution. As I mentioned, the difficulty in channel coding is how you deal with input distribution. Okay, and again we observe ds of what? ds of p multiplied by w. W is the channel, is fixed. P multiplied by w is the joint distribution induced by p and w. And P multiplied by PW. There are many things here I have to explain, and I haven't done so yet. Okay? There are many things here I haven't explained, and I will use this notation, P multiplied by W, to denote the joint distribution, okay, between P and W. Joint distribution induced by the input and the channel. I will use PW without the multiplication in between to denote the output distribution induced by P and W. So this notation is very nice because it looks like matrix multiplication. Alright, this is a vector and this is a matrix. You multiply it out, you get the output. Okay? P multiplied by W, XY. Okay? So this is this is not Feinstein's lemma, but this is Shannon bound. Alright? And this places a lower bound on the maximum number of code words I can transmit across a DMC, or across any channel for that matter, with error probability epsilon. Epsilon shows up here. Right? So you can take a further optimization, you can take a further supremum over eta. That's not necessary. So that's Feinstein's lemma. So in order for us to get a lower bound to the asymptotic expansion and to refine this object here, this expansion here, so that's what I call the first order term. These are the remainder terms. We can try to obtain the second order term here, right, and third order term if we wish, but this is not strong enough for third order asymptotics. Okay, so we can try to evaluate this when W is used n times, and let's see what we get. That is our agenda for the direct part. Okay, direct part means achievability part. Okay, good. So let us try to understand this. Okay, now once we have equipped ourselves with the asymptotic expansion for ds, this turns out to be relatively easy if we know how to choose p. Right? So you're free to choose p in any way you want, right? You choose any p, you get a further lower bound. Right? So let's choose p in the most sensible way. Right? This is a memberless channel. we are free to choose the input distribution. We should choose the capacity achieving input distribution. Okay? So let's see. Before that, maybe I will do a very short justification. Maybe not. Okay. Let us leave it at that. And if you're interested in the proof of Feinstein's lemma, or the average probability of version of Feinstein's lemma, you can read some reference. Okay? You can read Feinstein's paper or Hunt's book. So perhaps what is more interesting is for us to evaluate the asymptotic expansion, so I don't run out of time. Okay? So lower bound to asymptotic expansion. So I will use this board here to provide you the lower bound for the asymptotic expansion of log MAV star, Wn epsilon. Okay? So, as I mentioned, the most sensible choice for P, let us choose P, okay? The input distribution. Now it is a distribution on n letters, okay? Because we have replaced, let us assume we have replaced W with Wn. We are using the channel n times. So we can choose a distribution on n letters. Okay? So that's a distribution on the Cartesian product of the input space. Choose P to be product of Pi star. P star, that's enough. So this is an IID distribution. Okay? What is P star? I owe you the definition. P star is equal to the argmax, is equal to n, is equal to a distribution that optimizes mutual information. Now, folks, there can be many distributions that optimize mutual information. Alright? There can be many. But for the sake of simplicity today, let us assume that there is one. Okay? If there are many, we have to play some games again. Okay? Depending on whether epsilon is allowed to be greater than half or less than half. We will not go into that detail. So let's assume that this argmax here is unique. There's only a singleton. So you can choose one. Let us choose P to be the following. Then let us evaluate this object here. Okay? So this supremum here can be relaxed. This supremum here can be relaxed to just n-fold the IID distribution with distribution P. That's not the right way to say it, but so be it. So we can further lower bound this as ds epsilon minus eta Pn, okay, P star n if I may. Maybe we can write it this way. P star multiplied by W raised to the n, okay? So we replace P here by P star, W by Wn, P here by P star n and W by Wn. So we're using the channel n times. We have an input distribution that is IID distribution, P star n multiplied by P star W n as well. Okay, and as usual, we will take eta. By now you know the drill. We will take eta to be 1 over root n. And so this becomes log root n, half log n, if we may. Half log n minus. This is far from optimal. Okay? So now we have this very complicated looking object, but actually it's not that complicated. This is an IID distribution on x and on script x multiplied by script y. And this again another IID distribution on script x multiplied by script y. So we now appeal to the asymptotic expansion for ds, which says that the first order term is basically the expectation of the log likelihood ratio of this and that. The second order term is the variance of this and that, or the variance of the log likelihood ratio between this and that, right? And we have